Recording. Now we want to do the analysis of the same data set, the math and the school data set using R. Okay, so let me share my screen, and so we have started R, and the first thing that we have to do is we have to set our working directory. Okay, so desktop, MLM, and longitudinal. Okay, and then I will load workspace, which was there yesterday, and now the script that we are going to use is SPSS growth modeling.r. Okay, this is the script that we are going to use, and then we will do library multi-level. Okay, and we will do library foreign. Okay, and now I will read the same the horizontal data set using this command read dot spss. Okay, this is the function. So when you read this, it has read it in growth data horizontal, and so this has ID, SCH code, test 1, test 2, test 3, effectiveness, and SES. Okay, and then we have to now make it into vertical format. So what is the command? The command is make.udif growth data h, and what are the columns? 3 colon 5. So column number 3, column number 4, and column number 5, right? That is, these are the 3 columns that we have to make as vertical. So we are going to do that now using this make.unif command. Okay, and so the moment I do this, you see a new data frame has been created, growth data, and you see it has repeated effective SES, time variable has been created, and mult dv, this is the name, and you see 49.66, 50.09, 54.72, they have come in vertical order. So we have got our time variable, our mult dv, our SES, our effectiveness, and our ID variable, right? So now I'm just plotting to show are there random intercept and random slopes. Okay, we know this already, that there are random intercepts, there are random slopes. You see this is downward, there are random intercepts, and so on. Okay, this is a linear trend. So we will start to now do our analysis. The first is we will do the null model, which is null.model LME. And what have I written? I have written mult dv regressed on 1, random is equal to tilt 1, and it varies per ID. Data is equal to growth data. Rest is all something that we will keep writing. Okay, this is something that is important. There is one fixed effect, gamma 0 0. Okay, or in this case it is beta 0 0, and then random is equal to till there is random intercept. So let us run this command, and we do variance covariance. So we get sigma square u0 is 30.492, and sigma square r is 78.104. So what is going to be our ICC? Our ICC is going to be ICC1 is going to be 30.49298 divided by the sum. So if you run this, you get 0.281. This is what we had seen in our SPSS run also, and this is, I have written in the comment, ICC associated with math test score is 0.28. This indicates that 28% of variance in any individual's maths test score can be explained by properties of the individual, which is L2 variable. Now we will start to model time. Okay, so we will first model, let me write it here. We are first modeling the linear trend. So I am saying 1 plus time and random is equal to tilde. 1 varies with ID. Okay, very simple. So we will run this and we will do the summary. So what do we see? That the overall mean is 48, and then every 1 unit change in time, the math score increases by 4.23. Right? This is how we will interpret, and how we would is this significantly different from the null model? You see our fit statistics are coming here. Okay, now you can copy this in case you want to create a table like this. Okay, you can say this is SPSS run. You can say this is R run. Now you can simply copy these outputs. Okay, and when you are comparing, and you can say paste, and when you say paste, okay, it pastes it as a text. So you say text to columns, fixed, fixed, finish, right? So now you see what has happened. It has divided this into, so this is your model name. Okay, and you can say what is model.2. You can say this is modeling linear trend in time. Right, this is model 1 and 2 df. You get your AIC, and you get the, we can delete this. We can simply say this is our del deviance, and it is significant at p value less than 0.001. Okay, now we can go to our next, and I have said here model time, and now this is, let me write it here again. I will say model time, and this is quadratic trend. So what do I say? It is mult dv regressed on 1 plus time plus I time square, and random is equal to tilde 1 varies per id. Okay, it is still only random intercept, everything else is the same. I do this now and I do summary. Now what do we see? We see that this is the overall mean, and then this is, you can see this is your 1 unit change in time, and for time square we see that there is a negative coefficient minus 2.244, and it is also significant at p less than 0.05. If we were to compare this, okay, we see that this is significant at p less than 0.068. Okay, p less than 0.05. So again, you can see, you can simply paste it here, okay, and then again do data, text to columns, okay, next, next, finish, okay, and it comes here. You can simply paste these values here. Okay, so you can see what is your model 2. This is linear trend in time. This is quadratic trend in time. Now this is very easy with R. It does it automatically. Okay, and we can say this is your delta deviance. Okay, and we can center it, right? Now let us go to our next. Now that we have ascertained that there is a quadratic trend in time, now I am modeling slope variability. And at the moment I am modeling only random slope associated with time. So I have written, you see, everything else is the same. The fixed effects do not change. Mult dV is regressed on 1 plus time square. Random is equal to tilt. Now what is the difference? It is 1 plus time. So the time slope is also randomly varying. Okay, 1 plus time, and it varies per id. Everything else is the same. Or I could have written update model dot to be with random as this. Okay, but I am writing the full command so that you can know what's going on. And I say I run this now. And the software has estimated summary. Okay, and now you can see this is unstructured L2. That is why you have sigma u, sigma 1, okay, and sigma r, and then you have sigma u0 and sigma u1, right? So there is a correlation being estimated. This is unstructured L2. Now I can compare model 2, this previous one, with model 3, okay, where I say there is slope variability, okay, and what do I get? I get that this slope variability model, slope associated with time, is significantly better than random intercept model only. So let us copy this again now and paste it, and it will paste as a text. So I will go to data, text to columns, and fixed width, it is delimited. So you just say finish, and it has pasted it. I will copy both of these, Control X and Control V. This is my delta deviance. What is model dot to be? It is quadratic trend in time. And what is model dot 3? It is quadratic trend and variability in slope associated with time. Okay, so let me do text here. Right, this is my right. So these are my, this is my next analysis. Okay, and I can center these, align them. So this is better, and it has given me better result. This is a better fit. Now what do I write? I say model slope variability, linear as well as quadratic. This is where SPSS had given us an error. Now we are saying that random 1 plus time square, right? 1 plus time square. Okay, and all of these. So there is randomness associated with intercept. There is randomness associated with time. There is randomness associated with time square. All three of them have randomness. So there is random intercept, random slope for time, random slope for time square. Rest everything is the same. I run model 4. It is running, it is estimating. Okay, it will take time. Because now you have more parameters. It is unstructured L2. SPSS had given us a convergence error. R has run it. There is no issue. It has come back. Now when I do summary, okay, you see now you have sigma u0 u1, sigma u0, correlation between u0 u1, correlation between u0 and u2, and correlation between u0 and u1 and u2, right? So it has estimated L2 and it has given us the output. If I compare this with the previous model, I see this is a better model than the previous model. SPSS had given us, it had failed to estimate it. In R, we have been able to estimate it, and it is telling us that this is a better model than the previous model. So let me paste it in the Excel file, and I again do text to column, fixed width, next, next, and finish. Okay, let me paste these ratio tests here. Let me paste delta deviance here. Okay, what is my model 3? Model 3 is quadratic trend, variability in slope associated with time. What is model 4? I will say quadratic trend, variability in slope associated with time and time square, right? And this is my now new fit table. Okay, this is my new table. Now that we are, what is the stage? We have said that there is a quadratic trend, and in R we have been able to estimate that there is slope variability associated with both intercept time and time square, right? This has run properly and it has not given any error. Now what is the next step? We have to model error structures at level 1. The goal is to determine whether one's model fit improves by incorporating a correlational structure at L1 and also modeling heterogeneity in error structure. So the first is I am writing, now you see I'm writing 1 plus time square, random 1 plus time square, and correlation is equal to core sim. Okay, and form is 1 plus time. It varies over time with respect to id, right? And what is core sim? It says there is no structure actually. It is unstructured L1. You can say what is core sim. Let me write here. Core sim is equivalent to unstructured L1 correlation matrix, right? So this is what I have tried to do here. I'm saying this is the most complicated that can happen, and this is modeling the heterogeneity also, that there is going to be variance with respect to time as modeled over individuals, right? As it changes over individuals. This is the most complex, you can say, L1 correlation structure. At L2 we have anyways modeled. Let me write here in comment also. At L2, what are we modeling? Unstructured random covariance matrix, right? Similarly, yeah. So now I'm going to run this model.5 and let us see whether R is able to estimate it. Okay, I have written here also general correlation structure in the comment. Okay, our session aborted. Let us see why. Let us see if, okay, so R has also aborted this session. Let me just set my working directory again. And let me load my workspace. We are going to give a difficult time here. So growth data is here, right? So data has been created. So let us try modeling this and see if it is aborting it again. Okay, so now it has run. There is no issue. If I do summary, okay, it has given this, and you see it has formulated a matrix. There is time and time square. If I compare this with the previous model, model.4, okay, model.4 was not there because our session aborted. So model.4 is running. Okay, now I compare model 4 and model 5, and we see that actually there is no difference. These models are the same. If I model this kind of matrix and at L1, okay, so by default, let me also tell you, by default, let me also say here model dot 4, okay, let me say by default the L1 in R is scaled identity, okay, and L2 by default is unstructured. So this is what we have got here. Now if I compare this with model 5 and model 4, let me paste this here. Okay, again I say data, text to columns, next and finish. This is model 4, this is scaled identity, and model 5 is text. So L1 is also unstructured. Okay, we are seeing that there is no difference in the fit of the scaled identity is actually slightly better. AIC is smaller, BIC is smaller, but otherwise there is no significant difference in the two models. So we can say that scaled identity or no scaled identity or unstructured, there is no significant difference. Let us try another where you see I have now done what we had done in our previous thing. I have modeled AR1, right? So this is the residuals at level 1. The correlation of T0 and T1 is minus 0.223. At T2 it is 0.0933. At time 3 it is this much. So I have written, now the next is update model 5, and instead of core sim you bring in core AR1, which is auto regressive errors with lag 1, not to 1. Okay, so instead of doing this difficult correlation matrix which was unstructured, let me try out AR1. Okay, let's do this. Model.5a. It has run, no issues. Okay, summary I have got, and then I do ANOVA. If I compare model 4, which was scaled identity, and model 5a, again you see there is no difference. It is not less than 0.05. So again we can say that in in R we are getting scaled identity compared to autoregressive errors. The fit of the two models is the same. Okay, so let me copy this here, and for model 5a, let me say this is a. Okay, so they are actually the same in their fit. So scaled identity is as good. Now I have shown one more. This core, this is compound symmetry. Okay, I have written here compound symmetry. Let us try one more, which is compound symmetry. Let us, so this is summary and then model fit. Again, we see in the results there is no significant difference, and let me paste it. Data text to columns, finish, and then I paste it here. This is scaled identity, and this is component symmetry. So what is it that we are getting? We are saying that there is no significant difference again. Scaled identity at L1 is as good. So we are retaining scaled identity. We have tried multiple unstructured AR1 scaled identity, compound symmetry. We are not getting any fit which is better than. So this is what I have written. I have now removed correlation from the command because by default it models L1 as scaled identity, L2 as unstructured. So my next question is SES and not exposure actually, effectiveness, exposure to the teacher or effectiveness of the teacher significant in predicting intercept and slope variation, linear slope variation. So I have only brought in SES and effective, their main effects, and then the interaction with time and effectiveness. Okay, interaction of SES with time, effectiveness with time. So these are the two interaction terms. Randomness is still 1 plus time square, right? We run this. Okay, just give me a minute. I will close the window. Okay, so it is running. Yes, it has run. Now we do this summary, and you can see we have got our, okay, our fit. Let me first check, is it better than model? So just make this correction because we are retaining model 4. Okay, we will check this with model 4 and model 6, and we see that model 6 is significantly better than model number 4. So I will paste this in Excel, and I say data, text to columns, next, next, and finish, and I paste it here. Model 4 is scaled identity, and model 5 is, I will say, scaled identity. Model 6 is scaled identity, and then L2 predictors added for random slope associated with time. Okay, and we see this is significantly better than the previous model. Let me just arrange these. Okay, so this model, model 6, is significantly better than model 4, and it gives us lower AIC, BIC and deviance, and our delta deviance is significant. Fine. So we now say, okay, that means let us look at the effects. We see SES is not significant. It is not significant at p less than 0.05. Time and time square are significant. Okay, time into SES is significant at p less than 0.05, and time into effectiveness is significant at p less than 0.001. So we get this kind of a, and we can compare this with the output that we had got. Let me put this here, and our PDF, let me arrange it here, right? So now we see this is our intercept here is about 47.283. In here they had got 49.741. Then time was 2.409. Then time square was okay, this is the one, 2.307 minus 0.081. Here we are getting minus 0.244. SES is not significant. This is effectiveness is significant, and its coefficient is 2.43, and the interaction term is minus 0.154, and time into effectiveness it is 3.508. So about similar trends, there are slight differences in the coefficients. Okay, but in general we are getting the same kind of trend that we had got from SPSS, that there is a significant moderation of the time relationship by both SES and effectiveness. Now I go to the last one, where I want to show also the quadratic slope variation. So I say SES and SES effectiveness, SES into time, effectiveness into time, and SES into time square, effectiveness into time square, and randomness is for all three. So I run this command. So I have now both sets of interaction terms with time as well as time square, right? So I have SES into time, effectiveness into time, SES into time square, effectiveness into time square. Let it come and it should run. So R has allowed us to model the variation in intercept, variation in slope associated with time, and variance in slope associated with time square. And we are now testing the moderation effects. Yes, it has run. And so let me first compare it with model number 6. And you see, this model is also significantly better than model number 6, which was the previous model. So that means there would be some significant interaction terms with time square also. So let me just first paste this fit test, finish. Let me put this back, okay, and then model 6 is this, and model 7. Variability in slope associated with time and time square. L1 predictors added for random slope associated with time and time. So you see now this model is also better than the previous model. And let us now see the summary of this model. Let us look at the fixed effects. So intercept is significant, time is significant, time square is significant and negative, SES is not significant, effectiveness is significant, SES into time is not significant, effectiveness into time is not significant, SES into time square is not significant, effectiveness into time square is significant. So this comes out to be significant. So there is effectiveness which is moderating the effect of time on math performance, and the other three are not. So what am I doing? I am now dropping. So what are the terms that are not significant? SES is not significant. Its interaction with time and its interaction with time square is not significant. So I am dropping. So this is what I have written, dropping not significant, non-significant interaction terms. So I have dropped SES and I have dropped SES into time and SES into time square. What have I retained? I have retained effectiveness, and because there is an interaction term with time square, I have also introduced I have retained the interaction with effectiveness into time. So I run this model after dropping SES and its interaction terms. So it has run, and let us now do the summary. So now we have a simpler model where we have time, intercept, significant, time which is significant, time square, then effectiveness, and then you have effectiveness and time square which is moderated. If we compare the fit of the model, it is 7a is better than model 6. Then 7 and 7a, there is no difference between this model and where we had SES in the model. So we can actually say this is a parsimonious model and it gives a similar fit as the previous model. So that is what I have written, retaining model.7a as our final model. And this is the coefficient table associated with model.7a. Now if we want to run this model, okay, if we want to run this predict the, you can say, our moderation, okay. So what do I have created a data frame. So I first report the mean of SES, it is 0.037. So I create a data frame, I say time 0, 1, 2. Okay, it has three values 0, 1, 2. SES, I hold it at its mean value, and effectiveness, I first code it as 0, 0, 0 and then 1, 1, 1. So I create a data frame and I'm going to use this wonderful command predict. Using this data frame tdat uh, and using this model.7a, actually I could have even removed SES because in model 7a there is no SES variable, but anyways I have kept it, doesn't matter. So I use model.7a to predict my multidv. So I write this, use the predict command, and you can actually report these values also. So you have got these values and I can plot this in R also, right? So with effectiveness 1 and effectiveness 0. This is also the graph you can see in the book with effectiveness 1. Okay, it is a upward graph, and with effectiveness 0 it is downward. Here they have 1 is dotted line and 0 is a solid line, right? So we have plotted this graph using R. Otherwise you can very easily copy these values. That's the advantage of R. So we can say plotting moderation. So what do I say? Time is 0, 1, 2, 0, 1, 2. And then my effectiveness is 0, 0, 0, 1, 1, 1. And what are the values? My test values are, the first value is 46.92553. The second is 50.57162. The third value is 51.73302. The fourth value is 50.02837. 55.18150 and 61.47990. Now we have got these values, so we can do what we did yesterday. We do insert plot, okay, and I go to select data, I say add series, and I say effectiveness, effective is equal to 0. What are the series values? These are the three series values. I say OK. Then I press add and I say effective is equal to 1. What are the three series values? These are the three series values. And I press OK. What are the time horizontal axis labels? I say time 0, 1, 2. And I press OK. And then I change the layout. I go to this layout number 10 and I delete my chart title. I delete these. I delete these. I say this is math performance. This is, I say time. Okay, now I can change this access options. Okay, so if you see access option, it says minimum. In order to maximize and clearly view this, I can change the starting point to 30 instead of 0. And once you do this, you will see the graph starts to show a similar trend. You can change it to 40 also, and you see this becomes like this. Okay, and we can, okay, we can give it solid line, black in color. We can give this also black color. We can give this black color. We can give this black color and okay. Then for the chart, you see border, I say no line. And now this is ready to go in your manuscript. Okay, figure 1, interaction of effectiveness and time. Okay, this is what you will put in your research papers. Okay, this is your chart that is ready, because copying it from either R or from SPSS will not look very nice. So we typically use this from R. So this is how you can, so let me write this moderation plot using R output. Okay. So this is all that you can do. This is how you can do this longitudinal analysis in R. We did it. This is the end of this script. Okay, we did it in SPSS. We have done it in R. We have got this plot. Let me show you one last thing. I said I will show you how, if you have this, how you can plot it for your for the in SPSS also. So you have this coefficient. Okay, so let us, in case we were interested in plotting this uh, uh, again this kind of output math performance with time with respect to effectiveness, how will you do it using the SPSS output? So we will, let us create a table. We say time, okay, and we have auth time. So we give it name, again number. What was the coding? Let me remember that. I forget it every time. Yeah, minus 1, 0, and 1. Minus 1, 0, and 1. Okay, this is your time. Effectiveness, we know it takes two values, 0 and 1. So I will call this as effectiveness. This is your time. Okay, now the only variable left is SES, and we will hold SES at its mean. So the mean of SES is 0.037, which we got from, we had seen in R, when we ran this, we got 0.037 as its mean. Okay, which is what we know. Now, how would you compute values of test? So you have to key in these values of time and effectiveness and SES into this regression equation, right? So for example, what is the regression equation? The regression equation is test is equal to 49 point, let me round all of this to two decimal places. Okay, so what is your equation? Your equation is 49.67 plus 2.31 times auth time plus, or actually minus 0.08 auth time square plus 5.94 effective plus 0.07 SES plus auth time 3.51 into auth time into effective plus, or actually minus 0.15 times auth time into SES, right? This is our full regression equation. So in order to compute test, right, you have to key in these values. So we will need, or let me add another, uh, we will need auth time also. So let me just introduce another variable. So this is auth time is equal to 1 minus 2 and 1. So 1 minus 2 and 1. This is auth time and this is auth time square, right? So you need to create with all the variables that you will be needing in your data, right, in your this matrix. So what will be our test value for the first, you let's put this first coefficient plus auth time. Okay, open parenthesis. So I will say auth time multiplied with, what is the first value? This is the value, plus what is the next? Auth time square, what is its first value? This is the value, plus effectiveness multiplied with, what is its value? 0, plus what is SES? This is the coefficient and we have held SES at its mean. Then what is this? Auth time effective. So I will multiply auth time into the effectiveness value, right? Plus we say this multiplied with, sorry, parameter, this multiplied with the auth time first value multiplied with the mean value of SE. Yes, this becomes my first test value. Now I can codify all the, I will give absolute values to all the coefficients. So $C, $7, $C, $8. I am coding this because I will copy this formula, or I can demonstrate it writing repeatedly also. Okay, and then let's copy it for another cell. So $C, $7 is correct. Then for auth time, it is $C, $8, that is 2.31 into D19. This is correct. Then $C, $9 is correct, but auth time square value is E19. This is also correct. Then $C, $10 is correct. Then multiplied with F18. Now F18 effectiveness is F17, right, for 0. So we will replace this with F17. Then $C, $11 is correct. Okay, and this should be L11, okay, which is SES value. And then $C, $12 multiplied with D19 is correct, which is auth time. And then F18, instead of F18, it should be F17. And then the last one, $C, $13 multiplied with auth time, which is D19, multiplied with SES, which should be L11, which is SES value. So we get this value. Actually, we can codify even this is L11. So, and we are holding SES at its fixed value because we are not varying SES in this table. So we will hold it also at its fixed value. And I will press enter. Now I will copy this formula to next one, and I say $C, $7 is correct, which is our intercept. Then $C, $8, which is intercept of auth time multiplied with D20 is correct because this is the value of auth time. Then $C, $9 multiplied with E20. This is also correct. It is auth time square. Then $C, $10, and again it takes F18. Now F18 is not right because the value 0 is F17. Then $C, $11, and L, $11, this is all okay. Then $C, $12 multiplied with auth time, which is D20, is okay. And then effectiveness, it should be F17. And then auth time, so $C, $13 multiplied with D20 and L, $11, which is the mean value of SES. So we get the third value of, okay, now what do we get? This is actually, so yeah, yeah, there is one thing that we will need to, instead of writing auth time and auth time square, actually we should uh, I think we will have to keep it as uh, we will keep this as 0, 1 and 2. So this is my mistake. So you just keep this as 0, 1 and 2, and auth time square keep it as 0, 1 and 4. I think so. Let me let us try with both and then we'll see. This is a little bit confusing, so let us try it. So $C $7, then $C $8, and auth time should be uh, D18, and auth time square should be E18, and then effectiveness is G17 is correct, and then this should be L11. So I will make it $L $11, and then we have auth time. So auth time should be D18 multiplied with G17, and this should be D18 multiplied with $L $11. So this is computing for effectiveness is equal to 1. Let me paste it here. Now D19 is correct, E19 is correct. Instead of G18, it should be G17. Instead of G18, it should be G17. And D20 is correct, E20 is also correct. Instead of G18, it should be G17. And here also, it should be G17. Right. So now we have got for effectiveness is equal to 0, and for effectiveness is equal to 1. So we have got this as our right. So we have manually computed plugging in auth time square, effectiveness, SES, auth time effect into effectiveness, and auth time into SES values. In this regression equation, we have manually computed these values of test. Now what do? I bring in I insert my chart just like we had done earlier. We select data and I add the series, and we say effective is equal to 0. What are the values we have computed? These are the values we have computed. Okay, then I add a series and I say effective is equal to 1. What are the values I have? I have these values. Okay, and I keep this time as 1 to 3. It is okay, doesn't matter because I have not written 0, 1, 2 specifically. And then I change the layout. I delete these lines. I delete this, delete the title. Okay, I change the starting value of this axis. Axis options, starting value. I say 40. Okay, and now we can see this axis title. We say time, and this axis title we say math performance. And then I change my this line, change the color and make it dashed. This, change the color and make it solid. And then we say no border for this chart. So this becomes your chart again, ready for. Now you would see there is slight difference because in this SPSS output we did not have the auth times square, right, into effectiveness, auth times square into SES. So this was correct. What I had done is correct. You will put it as -101 and 1 -2 1, and you will get again. You can see that when effectiveness is 0, the rate is actually reducing a bit, and with effectiveness 1, it is also reducing slightly. But if we bring in the square term, we will start seeing the change in the parabolic structure also. So you can, if you have data in SPSS, this is what you can do. One last thing that I can also show you is you can also do one more way of plotting the data in SPSS, but the problem is in SPSS I will show you the issue. When you go to mixed models and you go to the last model run that we had done, so we had done this, we had auth times square into effective, auth times square into SES. There is a save button, you see, a save button, and now you can click on predicted values, okay, and you can say predicted values and residuals. So you say fixed predicted values, right? And only this is needed, fixed predicted values, okay? You don't need to do this, and say continue. And when you press OK, what will happen is you will get fixed predicted value, right? You see, it has predicted the test score. Now you can plot this using graph and legacy dialog box and say line and then multiple lines and then define, and you can say simply, you say fx predicted, and it will automatically, you press other statistic, it will take the mean. Category axis you put time, and define lines by you put effective. Okay, effectiveness was the moderator, category axis was time, and you say I want to plot the mean of these predicted values. Now let me paste this. I say plotting the graph using predicted values, okay, and let me also paste the other one where I had written save the predicted values, save fixed predicted. Okay, so I will write back predicted values. Okay, this was the command, and then this is plotting the graph. Now when I run this, you will get a chart like this. Okay, fixed predicted. So now you see there is a downward sloping line when effectiveness is 0, upward sloping line when effectiveness is 1. So this much is possible, but then how would you put it in your manuscript? Okay, that is a problem. That I don't know if it can be pasted. It will come like this. Okay, it will come like a picture. Now, in order to print this in a black and white paper, you need these kinds of plots. Okay, and that is where this SPSS plots may become challenging. Okay, not just SPSS, even R I don't like, because this is giving us this kind of a plot, and I want to do this in a black and white paper. So you need to learn get how do you plot this in SPSS using these coefficient tables, then giving specific values for the moderator, the variables that are there in your equation, and then computing these values by writing the full equation and computing these, and then using these values in your plots, and then pasting this back in your manuscript. Okay, so that is something that you will need to learn. Either you can do it in R, or you can do it in SPSS, and then use the coefficients and plot it. Okay, so this is what we have talked about in our uh, multi-level modeling. And just the last thing, okay, before I stop, multi-level modeling and longitudinal data analysis is the way we do multi-level data is has a lot of advantages. Missing occasion data are not a problem. I showed you that you can have unbalanced data structures, okay, and still you can estimate all the fixed and random effects. You can do growth modeling. Okay, rate of change may differ across persons. You can predict person characteristics. Easy to extend it to even 3 level models. In our course, in our workshop that we have done 2 levels. Okay, but in papers, very rarely, though, you will see they are also modeling 3 level datas. So time is nested under individuals, individuals are nested under schools. That becomes 3 level. Okay, or a student is nested within a class, and class is nested under a school. So again 3 levels. So you can do 3 level models also. Okay, and this Heck et al book is very nice. You can look it up uh, and learn further. Sample statistics, sample size guidelines. Rule of thumb was that you should have, as I said in my earlier class, that you should have in general close to 30 higher level, so L2 entities. So you should have those. But now there is, in 2002, there was this paper that was written. They have created a sample size calculator. I will show it to you. This sample size calculator, you can put in what is your sample size level 1, your sample size level 2, okay, your ICC 1, all these gamma 00, cross level effects. And you can see all of this, and they will give you what is the power of your analysis. Okay, so you can say how many level 2 you have, how many, what's the average level 1, what was the ICC, then level 1 intercept, then effect of level 2 variable on Y, cross level effect. So you can read these. Now you can understand these coefficients. If you plug in, you can get the power of your model or power of your analysis. Okay, so you can try with different level 2 sizes for your effect sizes, and you can see what's the power. In general, we say power should be greater than 0.80. Okay, so that is the new rule of the new way to kind of estimate your power. In general, you can remember that if I can have close to 30 level 2 entities, I can have a reasonable power. That was the earlier rule of thumb. Okay, so the last is, well, we have seen that random coefficient modeling, this multi-level models are good, but as they become complex, you may face convergence issues. Especially we have seen SPSS fails at a lot of places. When we were doing longitudinal analysis, it starts to fail at a lot of places. Okay, in general, we said unbalanced samples are possible to handle, but if you have too much of unbalanced, okay, you may not get significant effects. Okay, so that is, so minor variations may be okay, but too much of unbalanced data may create some problem as well. So these are just some warnings. Just keep that in mind, and you can always test it, iterate, run, and see what's going on. Okay, yeah. And I have all these references. I will upload this. Okay, whatever we have been talking. These are some good uh, text, a good reference material. There is a lot of material, that some papers that I have given you to read for both MLM as well as multi-level. Okay, go over it, go through these recordings, go through these examples, and you will get a sense of, and try these out, and I'm sure you will be able to at least do these runs better, understand what is going on better. Okay, so this is about it from my side. If there are any questions, let us take them now.